Hello friends, myself Dr. Nandakumar Raubawale from College of Engineering Ambazogai is going to discuss the fluid mechanics. So in previous lecture we have discussed about the numericals on Pascal's law and numericals on variation of pressure intensity if the fluid is static. Today we are going to discuss about the atmospheric pressure, absolute vacuum pressure, then absolute pressure, gauge pressure, vacuum pressure, classification of pressure measuring devices, and we are going to study in detail manometers, which is prescribed for your syllabus. Now, what is this atmospheric pressure? Atmospheric pressure is nothing but the force exerted by the envelope of air on the earth crust per unit area is known as the air pressure. Let us consider this is the earth, and this earth is surrounded with the envelope of air. So this air is having its self weight, and this self weight of this air acts against this earth crust. So its self weight is going to act over this earth crust, and this self weight per unit area, which is acting on the earth crust due to the gravitational force of attraction, is known as the atmospheric pressure. So air is surrounded with this earth on all the sides, and this air exerts pressure against this earth. So now this air which is present over the earth crust is having its density exactly at the earth surface or earth crust. It is going to be vary depending on the environmental conditions. So generally it is taken as 1.29 kg per meter cube at the earth crust, and if we move at the 12 kilometer from earth crust, the density of air varies, and that gets reduced, and which is about 0.3 kg per meter cube at the height of 12 kilometer from earth surface. So the density is not going to remain constant throughout the height above this earth. It is because of the temperature difference as well as the force of attraction due to gravity is going to vary as we move away from the earth crust, and because of that the density of air is also going to vary. So simply the atmospheric pressure is nothing but the force exerted by the envelope of air over the earth crust is known as the atmospheric pressure. So it is a self weight of envelope of air acting per unit area of earth crust is known as the atmospheric pressure. So now generally we calculate that is the pressure exerted by a static fluid is equal to rho g h. Rho is the density of air, g is acceleration due to gravity, and h is the height of air present over the earth crust. So we know acceleration due to gravity, g, that is 9.81, and h is the height of envelope of air. Say for example we consider it as 12,000 kilometer. So if we consider that as a 12,000 kilometer, we know h, and we can take air density. So this air density is not going to be fixed throughout the height. So at earth crust it is about 1.29 kg per meter cube, and at 12 kilometer from earth crust its density is 0.3 kg per meter cube, and also it depends on the environmental conditions. So from this we can find out the atmospheric pressure. So atmospheric pressure in bar is calculated as 1.0132 bar. So this is the atmospheric pressure, which generally we take as a standard atmospheric pressure measured with the help of device known as barometer. Barometer is the device used to measure atmospheric pressure. Now what is absolute vacuum? So now we consider one space where the air is present. Say for example this is a container, air is present, and if we use a vacuum pump to evacuate this air, so when we remove complete air from this space, so absence of matter in this space is known as a absolute vacuum. So if we remove complete air and if we measure this pressure, so that pressure is known as a zero pressure or absolute vacuum pressure. So when we use a vacuum pump to evacuate this space, from air, and if air is completely removed and nothing is going to remain, so in this space, and that is known as the absolute vacuum. So absence of matter or complete void space is known as the vacuum. So when we remove this air, empty space without presence of air or any matter, that is called as a absolute vacuum. So a void completely empty of matter is absolute vacuum or absolute zero pressure. Now coming to absolute pressure and atmospheric pressure, if we take x-axis and y-axis, along this x-axis, if we take absolute vacuum or zero pressure, this we can call as a absolute vacuum or zero pressure, where no matter is present or complete vacant space is there. And if we measure atmospheric pressure, which is above this absolute zero, so this pressure which is above zero vacuum or zero absolute zero or vacuum, so this pressure we call as a atmospheric pressure, which is exerted by the envelope of air on the earth crust. So this distance which we see here is nothing but the atmospheric pressure, or generally the pressure which is measured from absolute zero with reference to absolute zero pressure. This distance is called as a absolute pressure. Atmospheric pressure is the pressure measured from absolute zero pressure, so therefore this atmospheric pressure is also a absolute pressure. We can call this pressure as the absolute pressure also. Atmospheric pressure itself is a absolute pressure. Now coming to this next, what is gauge pressure and absolute pressure? So let us see here, we have seen this is the on x-axis, this is absolute zero pressure, and this is atmospheric pressure. From this zero pressure we measure the pressure known as atmospheric pressure, the pressure exerted by envelope of air. So the pressure measured above it more than this is known as the gauge pressure. So if we measure a pressure with reference to atmospheric pressure, it is known as a gauge pressure. So if we measure with absolute zero pressure, so up to this it is atmospheric pressure, and above this with reference to the atmospheric pressure, that pressure is known as a gauge pressure. But the sum of atmospheric pressure and gauge pressure, so if we measure completely starting from zero pressure, so it is nothing but a absolute pressure. So when we are going to measure the pressure with reference to vacuum pressure, absolute vacuum, then it is known as a absolute pressure. If we are measuring it with reference to atmospheric pressure, then it is known as a gauge pressure. So here absolute pressure is addition of atmospheric pressure plus gauge pressure is absolute pressure. Always if we measure pressure with reference to the absolute zero pressure, that pressure is known as a absolute pressure. If you are measuring with reference to the atmospheric pressure, then it is known as a gauge pressure. Above it, above atmospheric pressure, this pressure is known as a gauge pressure. So now coming to this next, vacuum pressure. So the pressure measured with respect to the atmospheric pressure below it is known as a vacuum pressure. So above this atmospheric pressure we call it as a gauge pressure, below this atmospheric pressure we call as a vacuum pressure. So pressure which is measured below atmospheric pressure is known as a vacuum pressure. So this pressure which is not above, it is below atmospheric pressure, is a negative pressure, and which is known as a vacuum pressure. Now if we measure this vacuum with reference to absolute zero from here up to here, so this distance we call as a absolute pressure. So any pressure which is measured with absolute zero, with respect to absolute zero, that is called as a absolute pressure, and if it is measured below atmospheric pressure, it is called as a vacuum pressure. So atmospheric pressure minus vacuum gives us absolute pressure. If we see here, this atmospheric pressure is up to here, so if we subtract vacuum from atmospheric pressure, then we can get again absolute pressure. So now coming to this next, we can see here, so this is absolute zero pressure, then we can call this as a atmospheric pressure, which is measured with respect to the absolute zero pressure, it is atmospheric pressure, and the pressure measured above atmospheric pressure is known as a gauge pressure. Addition of atmospheric pressure plus gauge pressure gives us absolute pressure. So absolute pressure is the addition of atmospheric pressure plus gauge pressure, or it is measured with reference to the absolute zero pressure, and the pressure which is measured below atmospheric pressure is known as a vacuum pressure. And if we subtract this vacuum pressure from atmospheric pressure, again we get this as absolute pressure. So absolute pressure in this case of vacuum, it is atmospheric pressure minus absolute pressure. So we can see here, this is in first case absolute pressure is equal to atmospheric pressure plus gauge pressure. In second case, absolute pressure is equal to atmospheric pressure minus vacuum pressure. So as this is a negative pressure, vacuum pressure is negative and gauge pressure is positive pressure. So we can see here the vacuum pressure and gauge pressure. If we add it to the atmospheric pressure, it gives absolute pressure. If we subtract vacuum pressure from atmospheric pressure, we get absolute pressure. So any pressure which is measured starting from this absolute zero, it is known as absolute pressure. If it is measured from starting from atmospheric pressure, then it is gauge pressure or vacuum pressure. So if measured above, then it is gauge pressure. If it is measured below atmospheric pressure, then it is vacuum pressure. So now coming to the measurement of pressure. So pressures are measured by various devices. So the devices are classified as first as a manometer and second as a mechanical gauges. So broadly, the pressure measuring devices are classified as a manometers and mechanical gauges. Then these manometers are again classified as simple manometers and differential manometers. So this manometer is classified as simple manometer and differential manometer, whereas mechanical gauges are classified as diaphragm pressure gauge, then bourdon pressure gauge, deadweight pressure gauge, bellow pressure gauge. Then these simple manometers are again classified as piezometer, then U-tube manometer and single column manometer. Piezometer, U-tube manometer and single column manometer. This differential manometer is again classified as U-tube differential manometer and inverted U-tube differential manometer. So for our syllabus, manometers is prescribed. So we are going to focus on manometers in our study. So the mechanical gauges are not prescribed in this syllabus for fluid mechanics. So therefore we are not going to have a focus on mechanical gauges. We are going to concentrate on manometers. So we'll study these manometers one by one. So now coming to the first type of manometer, simple manometer, in which we have a piezometer. So what this piezometer is? Say for example, this is a pipe through which some fluid is going to flow. It may be water, it may be oil, anything that is going to flow through this pipe. So we want to measure pressure of fluid flowing through this pipe. So to which we are going to connect one simple tube in at a point, and this liquid will enter into this tube. So this liquid will rise in this tube to a certain level H. So when it rises to certain level, because of its self weight of this liquid acts in the downward direction, and pressure of fluid PA acts against this self weight. So when this pressure of fluid flowing through a pipe becomes equal to the force exerted or pressure exerted by this fluid which has raised into this tube is going to become equal, then the rise of this liquid in this tube will stop. So for example, so here what we have studied is height of a liquid exerts pressure at the bottom. That pressure which we have seen is rho g h. Say for example, rho is the density density of liquid in pipe, g is acceleration due to gravity, and h is height of liquid in tube, that is in meters. So now the pressure of fluid acts in this upward direction PA, which is balanced by self weight or pressure exerted by this column of liquid in this piezometer. So therefore the pressure exerted by liquid against this pressure of liquid flowing in the pipe is balanced, so therefore rho g h. So this gives us the pressure in Newton per meter square. So this is the pressure exerted by liquid flowing in a pipe. Let PA be the pressure of fluid flowing in this pipe, circular pipe, to which this piezometer is connected. In this piezometer is nothing but a tube connected to this, and this liquid is going to rise in this tube to a certain level. So this level, if we know density of that liquid is known, then we can find out pressure exerted by this liquid. So this pressure exerted is equal to the self weight of this liquid acting per unit area in this tube. So this gives us the pressure of liquid flowing through piezometer. Now coming to this second type, that is U-tube manometer for gauge pressure. So if we want to measure gauge pressure, so there are two types of manometers. One is to measure gauge pressure, that is above atmospheric pressure, and another is the pressure which is below atmospheric pressure to measure vacuum. So first we are going to study manometer, which is used to measure the gauge pressure. So now here this is the image of U-tube manometer, simple U-tube manometer. So as we know, its name is U-tube. So similar to the piezometer, a U-shaped tube is connected to the pipe where pressure is to be measured. Say let PB be the pressure of liquid flowing in this pipe, and here there is a mistake in this diagram. So this pipe, this liquid enters into this tube, and this whatever is this dotted region is continuing up to this section AA. So here this is going to be a tube where same liquid is going to come up to here. So this heavy liquid is not there. Now when this liquid is flowing through this pipe to which U-tube manometer is connected. So in this U-tube manometer, this light liquid in the sense the liquid like water is going to flow, which has got pressure PB, which is not known. We are interested to measure pressure PB. So to balance this pressure, we are going to have the heavy liquid in this U-tube manometer. So when this liquid enters into in this tube, so this heavy liquid is displaced in the upward direction. So this heavy liquid may be mercury, Hg. So mercury is filled in this tube. So initially both level of mercury in both the limbs is going to be same. Say for example, this is U-tube manometer. Initially level of mercury in both the limbs is going to be same. So when this is connected to this pipe and pressure of this liquid exerted over this mercury, so level of mercury in right limb is going to rise, whereas the level of mercury in left limb is going to fall in the downward direction. So here this level moves up and this level moves down. So wherever this liquid enters up to this, and this heavy liquid moves in the upward direction. So now let us see that PB be the pressure of liquid flowing in the pipe whereas H1 is the height of light liquid above datum line. So we are going to take this lower level of this heavy liquid as the datum line or reference line. So a reference line or datum line A, H1 be the height of light liquid above datum line. Datum line in the sense AA line. Then H2 is the height of heavy liquid above datum line. So this H2 is nothing but height of heavy liquid above datum line. Then S1 be the specific gravity of light liquid. Then S2 be the specific gravity of heavy liquid. So specific gravity of say this water is S1, whereas specific gravity of mercury is S2. Then ρ1 be the density of light liquid. Say it is water or oil, something is going to flow here. So density of light liquid is equal to 1000 into specific gravity. So if specific gravity is known, we can find out density. Directly if density is given, need not to use this formula. Then ρ2 is the density of heavy liquid. It may be mercury or any other liquid. So if we know specific gravity, we can find out density of heavy liquid. So these are the things which we know now. Balancing these columns. So now what happens here, this liquid which is flowing in this pipe is going to exert pressure on this mercury, and this level of mercury is going to fall up to the datum. So on left side in this U2 manometer, in left limb of manometer, the pressure which is acting towards the right side is PB plus of the self weight of this liquid up to this datum line. So this self weight, so this is not going to be heavy liquid, this is replaced by light liquid. So H1 is the height of light liquid. So here rho G H1 is the pressure exerted in the left limb of manometer, whereas the pressure exerted in a right limb of manometer, if we take here, so this is going to be only H2 is the height of this heavy liquid. So pressure in this right limb is equal to rho of heavy liquid. So ρ1, we take this as ρ1 is the density of light liquid. So here we take ρ2 as the density of heavy liquid, G into H2. So when the pressure exerted in the left limb is equal to the pressure exerted in the right limb, then this system will be in equilibrium. Therefore equating this equation 1 and equation 2, we get for equilibrium equating equation 1 with equation 2, we get what we are going to get is PB plus of ρ1 G H1 is equal to ρ2 G H2. Therefore PB is equal to ρ2 G H2 minus of ρ1 G H1. So here PB can be written as PB is equal to ρ2 H2 minus of ρ1 H1, taking G as a common. So this will be the pressure exerted by the liquid flowing in this pipe. PB is measured in Newton per meter square. So this gives us pressure exerted by liquid flowing in the pipe. So when this pressure is above the atmospheric pressure, that is a gauge pressure, and gauge pressure is given by this equation. So if instead of flowing a liquid in this, if there is a vacuum created here, so the level of mercury, instead of rising in right limb, it will rise in the left limb and it will fall in the right limb. So we can see in this image, second image, so U2 manometer for vacuum pressure, measurement of vacuum pressure. We can see here. So if vacuum is created here, so pressure is PB, or pressure is in this pipe is less than the atmospheric pressure, then instead of rising this mercury in this right limb or heavy liquid in this right limb, so it will be sucked in the left limb. So level of mercury will rise in this left limb instead of right limb. Let H1 be the height of light liquid uh, and H2 be the height of heavy liquid in the left limb, and there is no liquid above this datum line in this right limb. So in the right limb there is nothing above this datum line in the right limb. So we can see here H1 is the height of light liquid in the left limb, and H2 is the height of heavy liquid above datum line. So this is height of light liquid, not above datum line, so it is just above the heavy liquid. And then rho S1 is the specific gravity of light liquid, S2 is the specific gravity of heavy liquid, then rho 1 is the density of light liquid, similar to previous case. Rho 2 is the density of heavy liquid. So now what is going to be there on the right side? Nothing. And on left hand side, the pressure exerted by the liquid in pipe, and then self weight of this light liquid and the self weight of heavy liquid are acting here. So now to write this equation, so pressure in left limb of manometer if we see here PB plus of rho 1 G, H1 is the pressure exerted by this much of height of liquid in the downward direction, then plus pressure exerted by heavy liquid in this left limb, that is rho 2 G H2. So pressure exerted in right limb, if we see pressure in right limb is equal to of manometer. If we see with reference to this datum line, nothing is above this datum line. So here on left hand side, so H2 is above this datum line, H1 is above this datum line, and pressure PB is acting from this liquid in the downward direction. So therefore, so pressure on right limb is going to be 0. So equating equation 1, so this is equation 1 and this is equation 2, we get PB plus of rho 1 G H1 plus of rho 2 G H2 is equal to 0. So PB is equal to, if we transfer these two terms on right hand side, minus G rho 1 H1 plus of rho 2 H2. So if we transfer these two terms on right hand side, those terms will become negative. Negative G minus G is taken common. Therefore PB is equal to minus G rho 1 H1 plus of rho 2 H2 Newton per meter square is the pressure exerted by this fluid flowing through B. So negative sign here indicates vacuum. So as there is a vacuum, this mercury rises in this left limb and mercury falls in the right limb. So now coming to this next manometer, single column manometer. So in this single column manometer, if we see here, it is the modified form of a U-tube manometer. So actually this is a U-tube manometer. In between this reservoir is fixed. So the area of cross section of this reservoir is about 100 times. It is about 100 times larger than the area of tube. Say area of reservoir is capital A and area of tube is small a. So this area of reservoir is 100 times larger than the cross sectional area of tube. So here initially this U-tube manometer is connected to this pipe A, where we want to measure pressure PA. So initially before connecting, the level of mercury in this reservoir was at X. So XX is the reference line when initially level of mercury was up to XX. So this level of mercury in right limb was just below it may be here at XX level. Both were at the same level because it was not connected to the pipe at a higher pressure. So when it is connected to the higher pressure PA, so pressure is exerted in this reservoir, and due to which so small change in the level of mercury is going to happen here. So this heavy liquid level falls below by distance delta H from the original level. So whereas the level of mercury in the right limb rises considerably because this cross sectional area is small, and because of which this is going to rise to the larger height, whereas cross sectional area of this is going to be higher. Therefore so a volume of liquid displaced here and volume of liquid to be displaced must be same. So whatever is the volume of liquid displaced in the reservoir must be the volume displaced in the tube. So as the cross sectional area is 100 times more, so this liquid will rise to the larger extent in this tube. So after applying this pressure, this liquid level falls to reference line YY or datum line YY. Before applying this pressure it was at XX, and after applying pressure it is at YY. So volume of liquid displaced must be in reservoir must be equal to the volume of liquid displaced in the tube. As the cross sectional area is less, so the level of mercury or heavy liquid will rise to considerable extent in the tube as compared with the reservoir. Now let us see the terms. Here H1 is the height of center of pipe above XX. So H1 is the height of center of pipe above XX initial level, so before connecting it. So then H2 is the rise of heavy liquid in right limb. So rise of heavy liquid in right limb after connecting. Then SP1 is the specific gravity of liquid. S2 is specific gravity of heavy liquid. Rho1 is density of light liquid. Light liquid in the sense liquid flowing in this pipe. Then Rho2 is density of heavy liquid, that can be a mercury. Then A is the cross sectional area of reservoir. A is the cross sectional area of reservoir, and small a is the cross sectional area of limb or this tube. Then PA is the pressure acting in this pipe, whereas delta H is the fall of heavy liquid in the reservoir. Initially it was at XX level, and after applying pressure it falls. So this fall of heavy liquid in the reservoir is by a distance of delta H, so which is given here. So this fall is delta H. Now we will consider this and we will simplify this here. So now fall in the heavy liquid will cause the rise of heavy liquid in the right limb. So here what is going to be happen here? Fall of heavy liquid in the reservoir. Fall of heavy liquid in the reservoir is the reason for this heavy liquid to rise in the tube. Therefore the volume of heavy liquid displaced in a reservoir is equal to volume of heavy liquid in right limb. So volume is given by area into fall in the heavy liquid is delta H, which is equal to area A into height H2. So it is going to rise by height H2. Therefore, delta H is equal to A into H2 divided by capital A. This is the rise in the level of heavy liquid in right limb. So delta H is nothing but a rise in the fall in the level of mercury in reservoir. So now we will consider the pressures exerted. So pressure exerted in this right limb, pressure in the right limb above YY. So above this Y reference line, we are going to consider Y as the reference line. Then the pressure in the right limb, pressure in the right limb above datum line YY can be given as, so density of this is ρ2, height which is moved up is H2 plus of delta H. So this is delta H above YY line. Total height is H2 plus delta H, rho GH we have to take rho 2 G into H2 plus of delta H. So this is, say, we call as equation number 1. So now pressure in the left limb. So pressure in the left limb is pressure because of this fluid PA. So pressure in the left limb above datum line YY is given by pressure PA is acting in the downward direction, whereas self weight of this liquid is also acting in the downward direction. Self weight is acting, that is nothing but rho 1 is the density into G into height of this liquid above this YY line is H1 plus of delta H. So total height from center of pipe is H1 plus of delta H. H1 plus of delta H. So we call this as equation number 2. So for equilibrium, equating these two equations, equating equation 1 and 2, equation 2, we get, so what we get, that we write here. So that is rho 2 G H plus of, H2 plus of delta H, rho 2 G H2 plus of delta H, equation 1, and which is equal to rho 1 G into H1 plus of delta H plus of PA. So equation 2, here we have PA plus of rho 1 G H1 plus of delta H. So PA rho 1 G H1 plus of delta H. So on simplification, or PA is equal to, we can write this as rho 2 G H2 plus of delta H minus rho G H1 plus of delta H So if we transfer this term on left hand side, it becomes negative. So here we have written it as negative. So now PA is equal to, if we simplify this as rho 2 G H2 plus of rho 2 G delta H minus rho 1 G H1 minus rho 1 G delta H. Taking these terms delta H on one side, we can rewrite this as delta H is taken as common, delta H rho 2 G minus rho 1 G, taking these two terms, plus we can write this as these two terms taking together, G is taken common, rho 2 H2 minus rho 1 H1. So this is PA, pressure exerted by liquid flowing in pipe. So we know delta H. So delta H just we have calculated, small a divided by capital A into H2, small a into H2 divided by capital A in bracket rho 2 G minus of rho 1 G plus of G rho 2 H2 minus rho 1 H1. So this is pressure exerted by liquid or a fluid flowing in a pipe PA, that is pressure PA is measured by this equation in Newton per meter square. So where this delta H is replaced by A H2 divided by A. So this is a single column manometer. Again, this single column manometer is classified as inclined single column manometer. So we are not going to study in much depth for this. So now we are coming to this next manometer, that is differential manometer. So U-tube differential manometer. What is this U-tube differential manometer? So the manometers which we have studied are going to measure gauge pressures till now. Now here the manometer which is not going to measure the gauge pressure, it is going to give the difference between pressures. So that is known as a differential manometer. So if we want to know the pressure difference at 2 points, so this U-tube differential manometer is used to measure the pressure difference at 2 points. Say for example, this is a U-tube manometer. One fluid is passing through pipe A, another fluid is passing through pipe B, and we want to measure the difference between pressure PA. PA is the pressure of fluid A and PB is the pressure of fluid flowing through pipe B. So at that time, what is the difference between pressure PA and PB can be measured using differential U-tube manometer, U-tube differential manometer. Now let what this A is, what is the fluid flowing in this, maybe same fluid or maybe different fluid. So right now we are going to consider there are two different fluids flowing in two pipes, pipe A and pipe B, and where we want to measure the difference. So one thing, important thing that we can see here, the level of pipe A and level of pipe B is not same. So the pipes, pipe A and pipe B are at different levels. So now let H be the difference of mercury level in U-tube. So here the lowest level of heavy liquid is taken as the datum line. So this is the heavy liquid, maybe mercury. So lower level of mercury is taken as datum. So above this datum, in right limb, mercury is going to rise above this. So this difference in the level of mercury is given by H. Then second thing, X. What is this? X is the distance of center of pipe A above this level of mercury, higher level of mercury. So above this is the distance X. Then Y is the distance of center B from the level of right limb of mercury. So right limb, from above this, it is measured from the level of mercury in right limb. In this X is also measured above the level of mercury in right limb only. Then rho 1 is the density of liquid flowing in pipe A, and rho 2 be the density of fluid flowing or liquid flowing in pipe B, whereas rho G is the density of heavy liquid. So here initially the level of mercury is going to be same. So when the pressure is applied, so as the pressure PA is greater than PB, so the level of mercury in right limb is going to rise. If pressure PB is greater, then this mercury will be displaced in left limb. So it depends, the level of mercury displacement depends on the relative pressure. If pressure PA is greater, then the level of mercury in the left limb will be lower, and in right limb it will be higher. If the pressure PB is greater, then this mercury will be displaced in the right limb and it will rise in the left limb. So it depends on the relative magnitude of PA and PB. So now we'll see the balancing of pressures. Taking here XX as the datum line, pressure above XX in the left limb datum line XX in left limb is given by, so in left limb pressure acting is PA because of this fluid. PA is the pressure acting because of this liquid in the downward direction. PA plus of the self weight of this liquid in this left limb is nothing but rho 1 G, and height of this is, total height of this liquid above datum line is H plus of X. So here rho G H is nothing but H plus of X. We call this as equation number 1, where PA is the pressure acting in the pipe, pressure of fluid acting in the pipe. Then pressure above datum line XX in right limb, which is equal to PB. PB be the pressure of fluid flowing in this pipe B, plus of self weight of this liquid, that is rho 2 G into Y. Then self weight of this heavy liquid is also acting in the downward direction. So self weight of light liquid B and self weight of heavy liquid, that is rho G is the density of heavy liquid into G into H. So we call this as equation number 2. For equilibrium, equating equation 1 and equation 2, we get equation 2, we get PA plus of rho 1 G H plus X, which is equal to PB rho 2 G Y plus of rho G into G. Rho G is the density of heavy liquid into H. So now taking this PA and PB on one side, PA minus PB is equal to rho 2 G Y plus of rho suffix G into G H minus of rho 1 G H plus X. So on simplification, we can rewrite, or we can take it as this term. So this can be the differential pressure, or we can simplify this rho 2 g y plus of rho g g h minus of rho 1 g h minus rho 1 g x. So here the term h, wherever h is going to contain, we collect on one side. So this can be written as h into g. H and g is taken common in these two terms. So rho g minus rho 1 plus of, so in these two terms g is taken common, g rho 2 y minus rho 1 x. So this is equation number 4. So PA minus PB, the pressure difference, the pressure of fluid flowing in pipe A and pressure of fluid flowing in pipe B. If we want to know the difference between the pressures, we can get it by using equation number 4. So now coming to this U-tube manometer, where the level of both the tubes is same. Here also H is the difference of mercury level or heavy liquid above this datum. So initially the level of mercury is going to be same when we connect it to the two different pipes at the same level. Then we can say that is the level is going to be shifted in a right limb when pressure PA is greater than PB. So this is going to be shifted in the right limb if PA is greater than PB. And if PB is greater, then this mercury will shift in the left limb instead of right limb. So H is the difference of mercury level above datum line in U tube, whereas X is the distance of center of mercury in the right limb, and Y is again equal to X here. In previous case Y was different, X was different. So here the level of distance of center above the mercury level in right limb is given by Y. So Y is the distance of center B from mercury level in right limb. So Y and X are going to be same here. X is equal to Y. Rho 1 is the density of liquid in liquid at A, whereas rho 2 is density of liquid at B. So the liquid is having different density, rho 1 and rho 2. So rho g is the density of heavy liquid. So now again we can write this equation. So the pressure above XX in left limb is equal to PA is the pressure exerted by this fluid plus of self weight, that is rho 1 g into this distance is y, but y is equal to x, so therefore we can write this as h plus x. H is this distance, h plus y actually, but y is equal to x, therefore we write x. So this is equation number 1. And pressure above XX datum line in a right limb is equal to, say, pressure is PB, pressure of fluid PB, plus self weight of this second liquid, that is rho 2 g into x, plus of self weight of this heavy liquid that is rho g into h. So equation number 2. So for equilibrium, we must equate equation 1 and 2. Equating equation 1 and equation 2, we get PA plus of rho 1 G H plus of X. So one thing we must remember, this is actually Y, but X is equal to Y, therefore we are taking this Y as X, okay, which is equal to PB plus of rho 2 G X plus of rho G into H. So transferring this PB on left hand side, we get PA minus PB. Transferring this rho 1 G H plus of X on right hand side, we can rewrite rho 2 G X plus of rho G into G H minus of rho 1 G H plus of X. So simplifying this, rho 2 G X plus of rho G H minus of rho 1 G H minus of rho 1 G X. Taking these two terms containing X on one side, taking terms containing H on other side, so we can rewrite this as Gx is taken common, rho 2 minus of rho 1, plus here Gh is taken common, Gh in bracket rho G minus of rho 1. So PA minus PB, we can call this as equation number say 3. So differential pressure measured using U-tube differential manometer having two pipes at the same level is given by this equation. So now coming to next term, that is U-tube manometer, differential manometer, which is rho 1 GX, rho 1 GX. Just a minute. Okay. If the fluid flowing in both the pipes is same, then this first term becomes 0. So if fluid flowing in both the pipes is same, then this first term is going to vanish, and only the pressure difference is nothing but GH rho G minus rho 1. So that is going to be going to depend on the type of fluid flowing in two pipes. If it is same, then rho 2 is equal to rho 1, therefore this first term becomes 0. Now coming to the inverted U-tube manometer. It is similar to the U-tube manometer which we have studied, only the thing is the U-tube is inverted. So how it is inverted, that is shown here. So this is the heavy liquid, and rho 1 is the first liquid flowing in pipe A, where PA is the pressure exerted by liquid in pipe A. PB is the pressure exerted in pipe B, whereas rho 2 is the density of liquid flowing in the pipe B. So where H1 is the height of liquid in left limb below datum line. So now datum line is taken here. and h1 is the height of liquid in the right limb below datum line. So whereas h2 is the height of the liquid second liquid below the level of heavy liquid in the right limb. Then H is the difference of the heavy liquid, light liquid. So here it is not taken as a heavy liquid, it is taken as light liquid. So in previous case, in ordinary U-tube differential manometer, heavy liquid, that is mercury, is taken. And in case of inverted U-tube differential manometer, light liquid is taken as the third substance for measurement of pressure. So H is the difference of light liquid. So H is the difference. So this is the light liquid. So difference of light liquid is given by H. Then rho 1 is the density of liquid flowing in pipe A, where rho 2 is the density of liquid flowing in pipe B. Then rho S is the density of light liquid filled in the inverted U-tube manometer, and PA is the pressure at point A, and whereas PB is the pressure at point B. So now looking at this, taking datum as XX, the pressure in left limb below datum, pressure in left limb below XX is given by, so pressure acting here in the upward direction is PA, P suffix A, but the self weight of this liquid is acting in the downward direction. So it is acting in the downward direction, therefore we have to take it as minus rho 1 G H1. So we call this as equation number 1. So after this reference, so this light liquid column gets balanced with the column of light liquid in the right limb. So up to this it is not required to be considered. Whereas pressure in a right limb below XX is given by PB, pressure acting in this is PB is the pressure in the second pipe, B pipe, minus of self weight of light liquid, that is rho G H into G. So this self weight is acting in the downward direction, minus this self weight of this second liquid is acting in the downward direction. So therefore rho 2 G H2. So this is equation number 2. For equilibrium, equating equation 1 and 2. We get PA minus rho 1 G H1, which is equal to PB minus rho G H G minus rho 2 G H2. So PA PB, collecting these two terms on left hand side, PA minus PB, which is equal to this term is transferred on right hand side, that is rho 1 G H1 minus rho 2 G H2 minus rho G into G into H. So this G is taken common, G rho 1 H1 minus rho 2 H2 minus of rho G G EH. So pressure difference PA minus PB is given in this inverted U-tube manometer. Rho G is the density of rho G or rho S. What is taken here? Rho S is taken. Rho S. So it makes no difference. So this rho g we can change here itself, rho g. Okay, so this pressure difference is given in this U2 differential manometer by this equation number 3. So we stop here. In next class we will simplify some numericals on manometer. Thank you.